Hi dear student, hopeful you are well and doing well. Me, this is me Daulat Khan, your mathematical modeling instructor. Today we discuss lecture number 11 which cover the week number 11 course. The topic is a spring mass system, how to model such kind of phenomena and then move to the solution of a spring mass system. As usual, before beginning to start the lecture, as usual, if you have any problem, you can feel free to contact us on WhatsApp group, or for live session, you can call us on our Zoom ID. So let's begin today's topic. Okay, spring mass system. So when we study the spring mass system, so we have two type of motion. The first one is free undamped motion, undamped motion, and the second one is damped motion. So first of all, we discussed the free undamped motion, undamped motion. So let's begin from where this phenomena is obtained and from where this phenomena is became. So Hooke's law. You all are familiar with this phenomena. What is meant by Hooke's law? Suppose that a flexible spring is suspended vertically from a rigid support, and then a mass m is attached to its free end. The amount of stretch or uh, elongation of the spring will be occur depend on the mass. It's mean when we attach a spring, a mass to rigid spring. So it's mean that the strength, the stretch of the spring will be depend on the mass of the object which we attach with the spring. Okay, masses with different weights stretch the spring by different amount. If we it's mean if we put different masses for a springer, so it will stretch the spring by different amount. I mean if we put if we put 20 pounds 20 pound mass weight, though maybe it stretch the spring up to 1 feet and up to, for example, up to 1 by 2 feet. And if we increase or decrease the mass of the object, so it will decrease or increase the stretch of the spring. By Hooke's law, the spring itself exert a restoring force F opposite to the direction of elongation and proportional to the amount of the elongation S. Elongation means that this is the length of the uh, spring. Okay, elongation means lambai. So this is the length of this spring. So by Hooke's law, this is directly the force which is a restoring force, or which is a opposite in the direction of mass weight, which is directly proportional to the elongation. It means the length of the string of the spring, and the also directly proportional to k, and where k is the constant of proportionality called the spring constant. Okay, the spring is essentially characterized by the number k. Using absolute of F, we see that if a mass weight 10 pound stretch a spring 1 by 2 feet, then 10 is equal to k 1 by 2. This means 10 is the force weight of the object, and k and s is the stretches of a spring, which is half feet. So this equation implies that the value of k, the value of spring constant, will be 20 pounds per feet. Okay, necessarily then a mass wing, say 8 pound stretch the same spring only 2.2 by 5 feet. Okay, if we decrease the mass of the springer, so it will decrease the stretchiness of the spring. Okay, now for the equilibrium position, we derive the spring mass equation through Newton's second law, which is F is equal to ma. So that's we here we write Newton's second law. When a mass m is attached to a lower end of a spring of negligible mass, a spring of negligible mass, in this the mass of the spring is negligible, it stretches the spring by an amount s. It means by F is equal to F is directly proportional to the stretching force, that is s, and attain an equilibrium position or rest position at which its weight is balanced by the restoring force Ks of the spring. Recall the weight is defined by W is equal to mg, and where m is measured in slugs, kilogram or gram, and g is the acceleration due to gravity. Maybe this is in slugs, in slug system, that is 32 feet per second and 9.8 meter per second square, in kilogram system and 980 centimeter per square. So these are the whole are the values of g as indicated in figure 5.1.1. Look at this one. This is a unstretched spring. Okay, and then we attached, we put some mass to the spring, so it stretch in the amount of s. Okay, and this is s is directly proportional to the amount of the mass, the amount of the weight which we attach to the spring. Okay, if we attach more mass to the spring, so the s will be more, the distance will be more, the displacement will be more. Okay, and if we attach small amount of mass, so it will be small. Okay, now and this, in this position, this spring mass system is in equilibrium position. Okay, this spring mass system will be is in equilibrium. So figure 5.1.1, the condition of equilibrium is mg is equal to ks. So in this position, the two forces are acting on the same phenomena at a time, which make the system is in equilibrium position. Okay, the first one force in downward direction, which is the weight of the object, that is mg, and the second force is the upward direction, which is the restoring force of the spring, whose values is ks, and which is in opposite direction of the weight. So that's here you can see that we write mg in positive sign while ks with negative sign. So this negative sign basically shows the direction, that is this restoring force in the is the opposite direction of the weight. Or in another form of this equation, we can write the mg is equal to ks. Okay, that's we write here. Look at this one, यहाँ पर हमने इसको लिखा है, और mg minus ks is equal to 0. Now suppose the mass on the spring is set in motion by given its initial displacement and elongation or compression and an initial velocity. Okay, let us assume that the motion takes place in a vertical line, that the displacement x of t of the mass are measured along this line such that x equal to 0, corresponding to the equilibrium position, and their displacement measured below the equilibrium position are positive. See figure 5.1.2. Okay, now look at this one. This is the equilibrium position of the given system. But if we stretch it, okay, if we stretch the spring, so it covers some distance, and that distance is equal to x. Okay, we can also compress in this direction, like this one. Look at this one. Okay, in this position, x greater than 0, it means we, if this position x is equal to 0 is in equilibrium position. But if we stretch the springer, so the distance will be positive, because this is in the direction of weight. So we take this as in positive direction, as we already take weight in the positive direction. So that we take this is a positive direction. So we say that this x is positive, and if we compressed this spring, so the value of x, the distance of the x will be negative, and the negative sign just show the distance in the opposite direction of the weight. Okay, yeah, it show the compression of the spring. So to construct a model that describe the dynamic case, we imply Newton's second law of motion, the net or resulting force, and which state that the net or resulting force of on a moving body of m is given by summation of fk. Any summation of all forces will be equal to ma, where a is acceleration, and where x, I will show you, f is equal to, look at this one, f is equal to ma. Okay, in simplest form. But acceleration is basically the rate of change, in velocity with respect to time. So it will be equal to dy dt, and further the velocity is defined as the rate of change in displacement, or in this case the displacement is x, and x is a function of t, because this displacement depend on time. This is the function of t. So the derivative, the rate of change in displacement with respect to t is equal to v. So we put this in this equation, so we will get m is equal to, a की जगह पर हमारे पास आ जाएगा d square. Okay, if we incorporate this v is equal to this value in this case, so we get the value of a will be equal to d of xt divided by dt. So in this case, as we write here, a is equal to d square x by dt. X is the displacement. If we further assume that the mass vibrate free of all other external force in free motion, the Newton's second law will give us, look at this one. This one is the net forces, weight. This is the look at in this one. This is the L plus S. L plus S mean length of the in this case S. S is the already stretched distance. Okay, so एक ये फोर्स भी अपोजिट डायरेक्शन में है, और दूसरा ये x जो फोर्स है ये भी है. So that's you write here minus kx plus minus ks. Yeah, in other words, look at this whole distance. We say that this whole distance is equal to s, and this one, look at this one, a from this point, s plus x. Sorry, that's not clear. S plus x. So the Hooke's law will be equal to, in this position, f, यह डिस्प्लेसमेंट जो आपके पास बन जाता है वो आपके पास बेसिकली x प्लस s बन जाता है. सो दैट्स यू राइट x प्लस s. ओके, so this one is equal to this one, minus kx plus s plus mg is the force of a weight, and this is mass. Okay, so this is equal to minus kx plus mg minus ks. Now we suppose that the weight of this is and minus ks is equal to 0. So this equation become like this one. In the next I write like this one. डीज ओके, बस ये सिंपल आपके पास ख़त्म हो जाएगा और सिंपल आपके पास एम डी आई स्क्वेयर एक्स डिवाइड बाई डी टी स्क्वेयर इज इक्वल टू माइनस के एक्स आ जाएगा. द फर्स्ट टर्म on the right hand side of equation is the restoring force of the spring. This represents the whole restoring force, and the negative sign indicate that this force acts opposite to the direction of motion. And the second term is the weight of the mass, which always act in downward or positive direction. So now this represent the equation of spring mass with a free undamped motion. Now differential equation for free undamped motion, by dividing one v by the mass we obtain the second order differential equation like this one. If divide this by m both sides, so ये m cancel हो जाएगा, यहाँ पर minus k by m into x आ जाएगा like this one. Okay, or this is equal to 0, or we put this k by m, k is also constant, m is also constant, so we take we put this is another constant, that is omega square. हमने इसको omega square कह दिया. Okay, और omega square this is the representation of the constant which we obtain from the k divided by m. So now this is a second order differential equation which represent the phenomena of such kind of spring mass free undamped motion. Okay, now equation 2 is said to describe simple harmonic motion or free undamped motion. Two obvious initial condition associated with 2 or that is x. Initial distance will be x naught. यहाँ पर दो conditions के साथ associate करेंगे. That will be the initial distance. What will be the initial distance at time equal to 0? So that will be x naught. Maybe in some cases it will be in equilibrium position, and maybe some cases that it have some distance. Okay, and the second one is x dash, which represent the velocity, initial velocity of the spring mass system. Okay, so this both condition will be associated to this सेकेंड ऑर्डर डिफरेंशियल इक्वेशन. और आपको ऑलरेडी पता है कि अगर हम इनिशियल बाउंड्री कंडीशन ऑफ सेकेंड ऑर्डर की सोल्यूशन फाइंड करते हैं, एग्जैक्ट सोल्यूशन, so we must know they have initially two conditions, that one on x and the other one on x dash. Okay, so यहाँ पर जो x है वो इनिशियल डिस्टेंस शो कर रहा है ऑफ द स्प्रिंग, and x dash is represent the velocity of the spring initially. The initial displacement and initial velocity of the mass respectively. Okay, now for example, if x naught greater than 0 and x1 is equal less than 0, the mass start from a point below the equilibrium position. Okay, अगर distance, look at this is very interesting. अगर initial distance हमारे पास greater than 0 from 1 है, look at this one. ये हमारे पास वो initial, ये हमारे पास इनिशियल है, यानी एक्स नॉट है. ओके, अब अगर एक्स नॉट मेरे पास ग्रेटर देन 0 है, ग्रेटर देन 0 मीन कि ये हमने स्ट्रेच किया हुआ है डाउनवर्ड डायरेक्शन में, सो इट हैव सम डिस्टेंस. ओके, इट हैव सम वैल्यू ऑफ एक्स, सो इट्स मीन कि यहाँ पर जो मास है वो फ्रॉम द डाउनवर्ड डायरेक्शन जो है वो मूव कर रहा है. And the second one is if x1 is less than 0, it means the initial velocity is negative. The mass starts from the point below the equilibrium position with an impart upward velocity. Okay, और ये जो velocity negative है तो it's mean in this position ये दोबारा जो है ना अगर इस position पे आ गया तो यहाँ पर इन्होंने कुछ distance cover किया होगा, और x dash लेस देन 0 का मतलब ये है कि इट हैव सम वेलोसिटी बट इन अपोजिट डायरेक्शन. ओके, यानी ये ऊपर की तरफ दोबारा उछल रहा है. सो इट्स मीन दैट इनिशियल इट स्टार्ट फ्रॉम दिस पोजीशन इफ वी हैव दिस कंडीशन. Okay, and if when x dash is equal to 0, the mass is said to be realized from rest. अगर x dash equal to 0, the initial they have no velocity, then we say that this the mass is from a rest position. But after that we have two conditions. If x, for example, if x naught is less than 0, the mass is released from rest from the point x naught until above the equilibrium position. ओके यहाँ पर फिर दो बातें हैं. अगर हम यहाँ पर x को ग्रेटर देन ले लें और वेलोसिटी को 0 ले लेते हैं, इक्वल टू 0 ले लेते हैं, तो फिर इसका मतलब ये है कि हमने यहाँ पर इसको स्टॉप किया हुआ है. ऑलरेडी वी स्ट्रेच द मास एंड नाउ वी गोइंग टू फ्री. हमने इसको छोड़ना है और इसका फिर वेलोसिटी आएगा. लेकिन अगर वेलोसिटी 0 है और ये एक्स नॉट जो है ना ये लेस देन 0 है, ये नेगेटिव है, तो इट्स मीन के वी स्ट्रेच्ड, वी कंप्रेस द स्प्रिंग. हमने इसको कंप्रेस किया हुआ है एंड देन वी हम इसको छोड़ेंगे ताकि ये फिर डाउनवर्ड डायरेक्शन की तरफ आ जाए. Okay, now the graphical interpretation, figure 5.1.4a illustrate the mass in example 2. Going to, okay, we did not discuss example 2, so it lives in there. But I want to, यहाँ पर इस figure का मतलब ये है, look at this one is basically the, this one is, ये हमने example किया भी है, last में किया है. बट इन दिस पोजीशन आप इसको देखिए, लुक इट, यहाँ पर हम जो इनिशियली है वो x आपके पास 2/3 है. ओके, इनिशियली x इज 2/3. सो इट्स मीन कि जो स्प्रिंग है वो यहाँ से स्टार्ट हो रहा है, यहाँ से स्टार्ट हो रहा है. अगर हम इसको फ्री कर दे, छोड़ दें, तो ये इस तरह मूव करेगा एंड फ्रॉम दिस पोजीशन टू दिस, एंड आफ्टर दैट इट विल गोज डाउनवर्ड एंड अप upward. So this is the geometry, yani the graphical interpretation of the free undamped motion of the spring mass system. The x is negative. Okay, in this position x is positive and x is negative in here, and this is the equilibrium position. लेकिन फिर इसको मैंने ये ग्राफ जो बनाए हुए तो इसको उल्टा किया हुआ है. दैट्स वी से दैट दिस इज़ पॉजिटिव, ये पॉजिटिव वाला ऊपर बनाया हुआ है और नेगेटिव वाला नीचे बनाया हुआ है. एंड ये ऑलरेडी आपको पता भी है कि दिस नाउन एज पीरियड एंड दिस नाउन एज अ एम्पलीट्यूड. ओके, सो नो नीड टू एक्सप्लेन. ओके, ये तो हो गया फर्स्ट केस, दैट इज फॉर फ्री अनडैम्प्ड मोशन. नाउ द सेकंड फिनोमेना in which we discussed the spring mass system for free dumped motion. And free dumped motion mean कि when we अगर मैं दोनों में फ़र्क बता देता हूँ कि अनडैम्प्ड मीन के उस पर कोई एक्सटर्नल फोर्स जो है ना वो अप्लाई नहीं हो रहा है और वो कंटिन्यूसली जो है ना एक रिदम के साथ, जिस तरह इस फिगर में गिवन है कि उसका एम्पलीट्यूड कम नहीं हो रहा है ना, वो हमेशा जो है ना इस तरह मूव कर रहा है. बट डैम्प्ड मोशन वी हैव सम forces which is acting on the motion of the spring, or it reduce the amplitude of the spring mass system. Okay, so that's we say that the free dump motion. The concept of free dump harmonic motion is somewhat unrealistic, since the motion described by equation 1 assume that there are no retarding force acting on the moving mass unless the mass is suspended in a perfect vacuum. Okay, for a free undamped motion, there will be at least a resisting force due to the surrounding medium. Okay, the figure 5.1.7 show the mass could be suspended in a viscous medium or connected to a dashboard dumping device. Dashboard dumping device ये एक device है which reduce the dump motion. Okay, look at this one. इससे पहले जो हमने फ्री अनडैम्प्ड मोशन पढ़ा था, तो उसमें कहने का मतलब ये था कि जो हमारे पास मोशन है वो किसी वैक्यूम में है, कोई एक्सटर्नल फोर्स उस पर असर नहीं कर रहा. Okay, but in this case we have some external forces, like in this case this mass is have some restoring force, yeah, we some uh, force some forces which is suspended in a viscous medium. Okay, ये एक viscous medium है जिसकी viscosity होगी. You better know about the viscosity. Air में भी viscosity है, fluid में की भी viscosity है, and so on. So but different material have different viscosity. So now what will be the differential equation for such type of phenomena? So let's begin the to model such type of phenomena. In the study of mechanics, damping forces acting on the body are considered to be proportional to a power of instantaneous velocity. Okay, this is the definition of damping forces, which is acting on a body are considered to be proportional to a power of the instantaneous velocity. In particular, we shall assume throughout the subsequent discussion that this force is given by a constant multiply of dx by dt. Dx by dt shows the velocity. So mean this damping force is the multiple of some constant with a velocity. When no other external forces are impressed on the system, it follow from Newton's second law that, okay. But in this case, we just consider the damping force. Okay, so the differential equation will become like this one. मैं यहाँ पर दोबारा बता देता हूँ. F is equal to ma. So the first force is its restoring force, which is minus k s या x, and we have another force that is damping, which is the some constant, and this constant is beta multiply with the velocity, and the velocity will be dx by dt. ये आपके पास क्या आ गया, ये फोर्सेज आ गए, सही ना, and ma उसी तरह md square x. So this equation will can be written as md square x by dt square is equal to minus kx minus beta dx by dt, where beta is a positive damping constant and the negative sign is the consequence of the fact that the damping force act in the direction opposite to the motion. Okay, or negative sign shows that this damping force is the opposite direction of the motion. Okay, divide 10 by mass, we find the differential equation of free damped motion is like this one: d square by d square x by dt beta by m dx by dt and plus k by m equal into x equal to 0. Now beta by m is also constant, k by m is also constant, so we call them 2 alpha and we call this another one is omega square. So look at this one, where 2 alpha is equal to beta by m and omega is equal to k by m. The symbol 2 lambda is used only for algebraic convenience because the auxiliary equation is like this one. Okay, ये फिर इसका auxiliary equation जो differential equation second order differential equation जब आपके पास आ जाए तो इसके solution के method है which जो आप लोग already differential equation में पढ़ चुके हैं. तो अगर इसका auxiliary equation इस तरह आता है, पहले जब आप इसको solve कर लेते हो, so the corresponding roots are will be m1 minus lambda plus lambda square minus omega square, और ये दूसरा इस तरह आएगा. So we can now distinguish three possible cases depend on the algebraic sign of lambda square minus omega square, since each solution contains the damping factor e power minus lambda t, where lambda greater than 0, the displacement of the mass become negligible at time t. Okay, सो ये तो डंपिंग फोर्स हो गई, बट वी हैव सम 3 केसेस बाय यूजिंग दिस फिनोमेना। ये मेरे ख्याल में आपको क्लियर होना चाहिए कि हम जब डिफरेंशियल इक्वेशन ऑफ सेकंड ऑर्डर आता है तो इसको कैसे, उसका ऑक्सिलरी इक्वेशन क्यों आता है, और इसको फिर सिंपली ये अलजेब्रिक इक्वेशन आता है इन द टर्म ऑफ m with the variable of m, and we can solve this by quadratic equation या quadratic फार्मूला या जो भी तरीका है quadratic equation का। तो हमारे पास दो रूट्स आते हैं और इस दो रूट्स के के मुताबिक फिर हम उसका वो जर्नल सोल्यूशन लिखते हैं। आई थिंक ये आप लोगों ने डिफरेंशियल इक्वेशन में डिस्कस किया है। सो रिवाइज differential equation. Okay, case 1, when the value of this one is greater than 0. Okay, in this situation the system is said to be overdamped. Overdamped means because the damping coefficient beta is larger when compared to the spring constant. Okay, now look at ये मैं यहाँ पर ज़रा explain करता हूँ। हमारे पास जो 2 लैम्डा है उसकी वैल्यू इस तरह है, this is equal to beta divided by m, and we have the value of omega square, which is equal to k divided by n. Okay, now lambda square, तो लेमडा अगर आप देखें तो ये 2 यहाँ पर आ जाएगा। सो लेमडा स्क्वेयर इज इक्वल टू, लुक इट इन दिस वन के, लेमडा स्क्वेयर माइनस ओमेगा स्क्वेयर इज ग्रेटर देन 0, सो इट्स मीन दैट वी हैव लेमडा स्क्वेयर इज इक्वल टू ओमेगा स्क्वेयर। सो अगर हम इसको देखें तो एम को कैंसिल को कैंसिल कर लेगा और m यहाँ पर आ जाएगा, बट इन दिस सिचुएशन बीटा इज ग्रेटर देन फॉर्म k। ओके, क्योंकि बीटा हैव सम वैल्यू, बीटा ए लार्ज व्हेन कंपेयर विद स्प्रिंग कांस्टेंट। बीटा जो है ना वो उसकी वैल्यू क्या होगी, लार्ज होगी, ठीक है ना। सो द करस्पॉन्डिंग सोल्यूशन विच इज ऑफ 11, अगर इस 11 को हम सॉल्व कर लेंगे तो हमारे पास ये सोल्यूशन आता है ना। तो ये आपके पास इस फॉर्म में आ जाएगा। दिस इक्वेशन रिप्रेजेंट अ स्मूथ एंड नॉन ऑसिलेटरी मोशन पॉसिबल ग्राफ। ये ग्राफ में यहाँ पर बता देता हूँ। इन दिस केस हमारे पास जो ओवरडम्प का मतलब ये है कि ये किसी पोजीशन पे, फॉर एग्जांपल यहाँ पर स्प्रिंग का पोजीशन है, ठीक है ना, एम का, ये किसी पोजीशन से बिल्कुल स्मूथली आएगा इस तरह, लुक एट, टू इक्विलिब्रियम पोजीशन। ओके, ये बिल्कुल स्मूथली जो है ना इक्विलिब्रियम पोजीशन आएगा, इसको कहते हैं ओवरडैम्प्ड। सो ये कब आएगा, व्हेन वी हैव लैम्डा स्क्वायर माइनस ओमेगा स्क्वायर ग्रेटर देन 0, एंड इफ वी हैव number second case, lambda square is minus omega square equal to 0, the system is said to be critical damping. Okay, now I want to explain critical damp, what is meant by critical damping and what will be the critical point, because any slight decrease in the damping force would result in oscillatory motion. The general solution of this one equal to this one. ये मैं बताऊंगा कि इसका क्या मतलब है। Some graph of the typical motion is given, ये figure मैंने नहीं लिखा है, लेकिन मैं यहाँ पर समझा देता हूँ। Notice that the motion is quite similar to that of the overdamped solution. Okay, quite similarly to the that of the overdamped solution. It is also apparent from 14 that the mass can pass through the equilibrium position at most one time. Okay, अच्छा यहाँ पर क्या होगा critical damping में, कि we have some oscillation, but one like this one, and after that we move to equilibrium position like this one, and it should be passed कम से कम एक दफ़ा जो है ना वो इस equilibrium position से पास होगा. Now this is the critical point. Okay, in a critical point mean that this is the highest amplitude. Okay, so this is mean the critical damping. Now in the third case, when the value of this lambda square minus omega square is equal to less than 0, in this case the system is said to be underdamped. Since the damping coefficient is small in comparison to the spring constant, the root m1 and m2 are complex, the general solution of equation will be this one. As indicated in figure, the motion described by is oscillatory, but because of the coefficient, the amplitude of the vibration will be n equal to 0 as t infinity.